show that these two things are equal. The integral from 0 to 1 of 1 over x to the power of x dx is equal to the infinite sum from 1 to infinity of 1 over n to the power of n. And so first, let me just copy down this definite integral 0 to 1, 1 over x to the power of x dx. That is equal to, from 0 to 1, change of base, right? X, change of base, e to the power of x log x. And then we have the reciprocal, so it is e to the minus x log x dx. Then it's Taylor expansion, 0 to 1, sigma. And from 0 to positive to infinity. N factorial, right, inside. So minus x log x to the power of n. Right. Then we do the integration. And so that is just I'm going to perhaps I'm going to switch order of the integration and infinite sum. So infinite sum from 0 to infinity. And first, let me do integration. 0 to 1 minus x log x to the power of n over n factorial dx. So that is just, I'm going to treat n as a constant because I'm integrating with respect to x. That is sum from 0 to infinity of, first I'm going to take out negative 1 to the power of n as well. Right, so right now I have negative 1 to the power of n over n factorial. And the integral is that I have 0 to 1 x to the n times log to the n of x and dx. Right. So I'm just going to have a look at this integral. This integral. 0 to 1 x to n log to n x dx. Of course, I'm going to treat which one as du, which one as dv. Right. Since the antiderivative of x to the power of n is easier to find compared with the log of to the power of n, so I'm going to treat log of to the power of n as u, right? And then find out its derivative. So u is log to the power of n, du, let's see, we'll treat dv, u dv, dv is x to the power of n dx. Right, v is simply its antiderivative, n plus 1, then n to x to the power of n plus 1. So that way du is simply, first of all, n times, then I'm going to multiply the chain rule. So in the end, I'm going to have to multiply by the derivative of log x, that is 1 over x, according to the chain rule. Then I'm going to take down the power, n log to the power of n minus 1 of x dx. Right? So that way this integral, right? This I is equal to uv n plus 1 x to the power of n plus 1 log of the power of n x from 0 to 1. The minus integral 0 to 1 v du v du, u dv, v du, this times that. Right. The n plus 1, and x to the power of n plus 1, x to the power of n. Right. Simplify with this x down here. So now I'm going to have n up here, and log to the power of n minus 1 of x dx. So since this part, first let me have a look at the let me have a look. Since 1 doesn't have a problem, right? If I replace 1 into here, right? Log of 1 just 0. 0 times it, so the whole thing becomes 0. So the problem is what happens with 0, right? So when x approaches 0, the log will approach negative infinity. So it's a matter of whether x approaches 0 faster, or is it that the log of x approaches negative infinity faster, which have a bigger impact. So I'm looking at the simple case of x times log x as x approaches 0. Right? So does the limit exist? So right now I'm looking at log of x over 1 over x, right? It's the same thing, right? As x approaches 0. So the bottom is approaching infinity, right? Maybe perhaps from 0 from the right-hand side, right? Perhaps positive infinity. So the top doesn't matter. So L'Hopital's rule. All right, so I can look at the derivative. Right? Derivative of that is just negative x to the power of 2, 1. Right? That is just negative x, right? So as x approaches 0, this will of course approach 0. Now, so which means this approaches 0 as x approaches 0, right? Meaning x approaches 0 faster than log x approaches negative infinity, right? So in this case, so x to the power of 1 taken out, x to the power of n times log to the power of n. So x times log altogether to the power of n, still approaching 0. And also x also approaches 0. So the whole thing approaches 0. So 0 minus 0. Like I said, 1 goes into x, right? Just 1 times 0, right? So we just have this one, this part. Okay, so now I have this I, so I represents this integral, right? I'm going to multiply by constant later. I'll explain the legality of switching the order between infinite sum and integral later. First, this integral. So this integral, negative. So negative 1 times, I'm just going to take out the constant, n over n plus 1. Integral from 0 to 1. X n log n minus 1 x dx. So likewise, I'm gonna choose x to choose log u, right? U log to n minus 1 x. Right, because it's easy to find its derivative compared with its antiderivative. That's why. So u dv is dv x to our n dx. So that way, du is easily just like a chain rule. In the end, I'm going to multiply by 1 over x. Right? Then take down the power. N minus 1 times log n minus 2 x dx. So v is again n plus 1 x to the power n plus 1. Right, so that this I is equal to negative 1 times n over n plus 1 times bracket uv so x to the power n plus 1 times log of n minus 1x from 0 to 1. So like I said, this is similar to this. Like I said, x times log x approaches 0 as x approaches 0. So again, so we can take out x to the power of 2 out here. So x times log x altogether to the power of n minus 1. Still approaching 0. As we substitute 0 in here. Right. 1 goes into x, doesn't matter. So log of 1 becomes 0. Right. So 0 minus 0. So this is gone. And also integral, so minus integral from 0 to 1 v du n plus n minus 1 times x to the power n log n minus 2x dx. So that is I is, so I'm going to multiply this constant, right? This becomes 0. This constant multiplied by this, but this constant also taken out, and negative sign out here, right? So negative 1 times negative 1. Negative 1 to the power of 2. Here's the pattern. And the denominator, I have n plus 1 square. And on the top, I have n times n minus 1. The integral 0 to 1 x to the n times log to the power n minus 2x dx. Okay, so right now the pattern is kind of clear, right? We do the integration by parts twice. Then we have negative 1 to the power of 2, right? And n plus 1 to the power of 2, and n times n plus 1, then, right? After we did it twice. Now, if we do it 3 times, right, we can expect to have negative 1 to the power of 3. Down here, we have n plus 1 to the power of 3, and we have n times n minus 1 times n minus 2. If we do it n many times, right, then eventually we can have I will eventually become negative 1 to the power of n, right, n plus 1 to the power of also n, right, it's consistent. So we have n times n minus 1 times n minus 2 all the way. So n terms, right, it must be n factorial, right, n times all the way down to 1. Must be n factorial. So we still have the integral 0 to 1, right? And also, I always have x to the power of n, right from the start. And no matter how many times I do the integration by parts, always have right, x to the power of n. X to the power of n, right? So still x to the power of n. But the power of log is just keeps reducing, right? Twice, 3 times, n times n minus n 0, right? So 1, just dx. This is easy. Negative 1 to the power of n, n plus 1 to the power of n factorial times n plus 1 x to the power of n plus 1, 0 to 1. Right. Negative 1 to the power of n. Right. That is what? That is 1 over n plus 1. Right. So the bottom becomes n plus 1 to the power of just n plus 1. Right. N factorial. And so like I said, the integral I, right, so this integral, so there is this integral is equal to this. So I still need to multiply by this constant, then do the summation. So right now I'm looking at this constant multiplied by this, and then do the infinite sum. Right, so I'm looking at infinite sum from 0 to infinity of n factorial, negative 1 to the power of n times negative 1 to the power of n over n plus 1 to the power of n plus 1 times n factorial. Right? So n factorial, negative 1 to the power of negative 1, negative 1 to the power of 2n, 1. Right? Just 1 on top. And that is equal to, I'm starting from 0. Right? 0 plus 1. I'm starting from 1, in other words, if I replace n plus 1 with n, right? N to the power of n, 1 over. Starting from 1. Right? So right now I'm done done proving this identity. So the legality, why can I switch the order between infinite sum and integration? Right? The reason is because of uniform convergence. Uniform convergence. First of all, I'm going to say that I'm going to take this functional sequence, general term of the functional series. I'm going to have a look at the absolute value, n factorial, minus x log x to the power of n. Right? Absolute value is equal to n factorial. Absolute. Perhaps I'll just use x to the power of n times log power of nx. So like I mentioned earlier, the x times log x approaches 0 as x approaches 0. Using just L'Hopital's rule, this is easily verifiable. And so therefore, so x times log x altogether to the power of n still approaching 0. Right, that is easy to easy to show. Right? So x times log x altogether to the power of n. Right? So when x is equal to 1, then we have x times log x is equal to 0. So this has no problem, right? So the only problematic point is that when x is nearby 0, right, so it cannot equal to 0. So nearby 0, like we require x to be positive, right? Nearby 0, like I said, it's approaching 0, right? The whole thing is approaching 0. So which means nearby the point 0, this function, right? Function nearby 0, approaching 0, functional value approaching 0. So meaning nearby 0 function is bounded. There is some neighborhood, function is bounded. Outside of this neighborhood, all the way to point 1, right? It's continuous everywhere, closed interval, continuous everywhere, but therefore also bounded. So overall, from 0 to 1, the function is bounded. I mean, this function, right? So x times log x, absolute value is less than or equal to some positive constant. It has nothing to do with the value of x. All right, then we can say that n factorial x times log x to the power of n, right, also absolute value. Right, since this absolute value is bounded, therefore this absolute value, right, of course bounded also, right? Take the absolute perhaps value inside, right? So replace this with m to the power of n. Right now I'm holding n constant, right? Later I'm going to let n approach. So right now n constant. and the inside is bounded. So m to the power n. So right now I'm looking at this infinite general term of an infinite series. Right, how do we decide if it's convergent or not? Right, how do we, like for example, n from, so I'm looking at perhaps from 0 to infinity. Right, how do we determine that this infinite series is convergent or divergent? Right, perhaps use ratio test. Ratio test. Right, divided by the previous term. Right, previous term is so multiply the reciprocal of the previous term. Right, n minus 1 factorial. N to the power of n minus 1. That is equal to just n, then capital M over n, approaching 0. Right? So 0 is less than 1. So according to ratio test, D'Alembert test, so this infinite series has to be convergent. Therefore, the absolute value of the general term of this functional sequence is less than or equal to than some general term of an infinite series that's convergent. Therefore, according to Weierstrass test, so this functional series has to be uniformly convergent. So therefore, it is legal.